So now we're going to talk about stable and radioactive isotopes. The lesson that goes along with this, you saw, was called the island of stability, or isotopia, which gave you a graph of the elements and what stable isotopes they have. Now, we're going to start by looking up, sorry, hold on one second. Okay, so we're going to start by talking about the four forces of nature. So the one that we're most probably commonly aware of is gravity. So this happens, and it's only attractive. It's the attractive force between any two objects with mass. Now, you talked a lot about gravity in physics last year. Gravity can only be attractive. If gravity were repulsive, then we would be shot out into outer space and continually accelerating until we felt the force of another massive object. So we are lucky that gravity is attractive, and it holds us to the surface of our planet. The other one you learned about in physics was the electromagnetic force. And this is, our idea of opposites attract and likes repel. This is super important for us in chemistry, the one we'll talk about by far the most. When you get further along in your chemistry studies, so you'll see that there are two other forces. The first is the weak nuclear, and it's not important for today. It has to do with some decay. And then we have the strong nuclear. Now, this is what we're talking about today. We're only going to talk about the strong nuclear force in terms of the type of stuff we're doing today, which the strong nuclear causes protons and neutrons to stick together. The only time I ever want you to talk about the strong nuclear force is in terms of protons and neutrons sticking together / we'll call it attracting one another. The technical reason why for this, it has to do with the component quarks that make up protons and neutrons. You don't need to know about that. You can ask me about that on the side. But what I want you to be able to take away from today, the four fundamental forces, gravity, electromagnetics, the weak nuclear force, and the strong nuclear force, is that the strong nuclear force is what causes a nucleus to stick together. You have so many protons. Well, you have protons in the nucleus. And you would expect that those protons, those positive protons, because of electromagnetism, to push each other apart. Well, that doesn't happen because of the strong nuclear force. It causes protons and neutrons to stick together. If there was not the strong nuclear force, the only type of atom we'd have in the universe would be hydrogen, because everything like from helium on would have nuclei that had repulsive forces in them that were too strong, and they would just break apart. So the interesting thing about stable and about these four forces are the range of them increases towards the top, increasing range. So gravity can be felt over enormous distances. Electromagnetics, think about if you're rubbing your feet on the ground and you build up a lot of charge. If you're far away from someone, you can't shock them. You have to get pretty close to shock them. Electromagnetics only works over a pretty small radius. The weak nuclear force is less of a radius than electromagnetic force. The strong nuclear force only works over the size of about the nucleus. So once you get any distance outside the nucleus, the strong nuclear force does not work anymore. So like we don't feel the strong nuclear force. If I'm touching the table, I can't tell what the strong nuclear force is. But as I move down the table, they get stronger. So the strong nuclear force is many, 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 many times stronger than gravity. However, it only works over an extremely short distance, like the size of the nucleus of an atom. So just like the electromagnetic force is stronger than gravity, but works only over a short distance, strong nuclear force is even stronger than any of those above it, but works over a very, very, very short distance. Now, in order to keep the nucleus stable, we need a balance between to keep a nucleus stable, we need a balance. So the strong force holds the nucleus together. Electromagnetic forces push it apart. Pushes/repels. So you can think of, in this case, neutrons are the glue. That holds the nucleus together. And for a nucleus to be stable, there needs to be the right ratio of protons to neutrons. This is the little ratio, that those two dots are the little ratio sign. So if you have too many protons, well, the electromagnetic force takes over and it pushes apart. If you have too many neutrons, you got too much glue and you're just left with a big, huge mess that won't stick together. So it needs to have the right ratio of protons and neutrons to be stable. Once you get outside of that correct ratio, you get what's called a radioactive isotope. Use red. And this is a nucleus with either too many neutrons, too many protons, or a nucleus can get just too big. Imagine you're trying to glue stuff together. Well, eventually, there's not going to be enough glue. All the glue in the universe won't work to make something stick together if it gets too big. And this is true of atoms, too. So a nucleus with either too many neutrons, too many protons, or just too big. Now, if you look at your periodic table, I'll give you a few seconds to take it out. Take out your periodic tables. You'll notice that the elements towards the bottom of the periodic table have average atomic masses that are in parentheses. I think yours has them in parentheses. This means they're radioactive because these nuclei are just too big. They can't get the right ratio of protons to neutrons. And in fact, I don't know what number your periodic table goes up to, but after a certain point, scientists have not even been able to synthesize these in a man-made way to create them because the nuclei are just too big and they can't get it to stick together. So a radioactive isotope will decay. Eventually will decay. And it decays by shooting out little pieces of itself. Until it becomes unstable. So it'll keep decaying until it becomes a stable nucleus. Now, as it's shooting out those pieces, it's also shooting out energy. And the energy it's shooting out is why nuclear bombs are so dangerous. It's because it shoots out gamma rays. So as it breaks apart, it loses energy as well. It releases energy in the form of gamma rays. And unlike the Incredible Hulk, gamma rays don't turn you into a super strong green monster. They give you cancer. So you don't really want to be around too much of a material that's decaying. So wrapping up, the question of the day was, what types of isotopes do the various elements have? Well, each element found in nature has between 1 and 10 naturally occurring isotopes. So remember, the elements that aren't found in nature are radioactive. They're either not the correct ratio of neutrons to protons, or they're just too big. So the neutron to proton ratio is an important factor in determining stability. Atoms with small masses have a ratio of about 1 to 1, and then as you go up, you require more neutrons per proton, more glue, so you get a neutron to proton ratio of about 3 to 2. You don't need to remember those numbers. Some elements have isotopes that are radioactive. The nuclei are unstable and decay over time. Okay.